I'm Tim Ventura, and we're joined today by Dr. Robert Sutor, a quantum computing subject matter expert, Vice President and Chief Quantum Advocate at ColdQuanta, and author of Dancing with Qubits, which follows his publication of several other computer science books. Dr. Sutor has a BA in mathematics from Harvard and both an MA and PhD in mathematics from Princeton University. His career includes over 40 years of technology industry expertise, including 2 decades of senior leadership positions at IBM. So, Bob, welcome back, sir. It is a pleasure and an honor to have you with me today.
Thank you. It's great to be back. And let me just give you an update. ColdQuanta is the historic name. The company is called Infleqtion now, with a Q. Yet, it's harder and harder to find company names that you can put a Q in the middle of in this field.
Ah, okay.
So every time someone says inflection point, I got a marketing check. So.
Today we are discussing your paper entitled Crossing the Quantum Chasm, Moving from Little Quantum Computers to Practical Networked Quantum Systems. And I felt this was really timely because quantum computing is back in the headlines. We're not going to go too deep into the headlines, but I did want to touch on some of that. Before we dive in, I want to start by asking if it would be fair to describe this new paper as what we might call a reality check on the current state of quantum computing.
Yes, and that's why I wrote it. I'm very optimistic about quantum. I mean, quantum in general, quantum technologies, they're coming along well. Quantum computing, we've seen some terrific results over the last few weeks from in neutral atoms and superconducting and so forth. But how do you separate out the idea that you're getting better and better smaller computers from actually getting big enough, powerful enough computers to do the sort of work that all these great use cases seem to promise? So when we talk about pharmaceuticals and new batteries and optimization for financial services, well, just how large a computer do you need to do these types of things? And unfortunately, let me tell you, it's not next week, it's not next year, but if things keep going well, we will get there, but there's work to be done. And that's really the foundation of the paper. How do you go from these small computers where we are seeing good progress, but to the sufficiently large ones that we will really need?
Well, and so I've gone through this paper 2 or 3 times, and what you outlined in this, there are so many areas that need significant work. I was really amazed. And, I just want to give, again, a credit to your subject matter expertise. These are things that I have not, some of these I haven't heard of since college. So it's going way, way back. But you really dug down in it. And I'm going to try and get links up to that just so that people can learn what some of the obstacles are. Let me go into the big headline last week, which was IBM's announcement of the Condor quantum computing chip. So this one has 1,121 superconducting qubits, which is about 2.5 times more than the 433 qubit Osprey chip they unveiled last year. Again, I don't want to get too deep into IBM, but it is worth mentioning that this rate of development far outpaces Moore's law in semiconductors, which anticipates doubling every 2 years. Do you see this kind of rapid development happening across the entire quantum computing industry, or is this only in some of the leading companies like IBM?
Well, first of all, kudos to my former colleagues in IBM. IBM Quantum, they said they were going to do this. They laid out the roadmap several years ago, and they hit their target. So congratulations to them. Well, your question actually opens up one of the points I make in the paper. IBM and others have had what I call quantum cores. You can think of them as chips. In neutral atoms, we actually arrange these atoms. You can imagine a very tiny checkerboard where we put the atoms and they act as qubits. When we do ions, we move them around in different ways. But the idea is that there's some maximum number that we can put on a chip or in one of these checkerboards, as I said. I call this a quantum core. And I don't think we're going to continue to see cores, at least for superconducting, that get too much bigger. Because the number of qubits you need is much more than 1,000, right? I mean, in the paper,
Yeah.
I say, to be practical, we need between 100,000 and 500,000
Yeah.
qubits.
Yeah.
You're not going to get that in a chip. Now, maybe some of the other technologies like neutral atoms may get you up 10,000, maybe a little bit bigger. At some point, you have to modularize, right? You have to say, I have a chip, I have an array, I have a trap. That's a core, just like in your laptop, in your phone. You have multiple processing cores. You need multiple quantum processing cores that we then connect to each other. And that's how, almost like Lego blocks, quantum Lego blocks, we will put them together to get bigger and bigger computers. However, we don't know how to connect them very well yet. We don't know how to do that in general. So while we can create these slightly bigger and slightly bigger cores, we're worlds away from how big we need to get to. And I think we better start paying a lot more attention to connecting these cores. Probably in many technologies via optical. So we go to photons, we send the photons to something else, we transduce, that's a fancy word, it basically means moving quantum states from one place to another, and then we can use them elsewhere. We need this for networking. We're going to need it to create bigger quantum computers. We're going to need that to connect quantum computers to quantum memory. We're going to need it to connect sensor data in quantum form to quantum computers or quantum memory. So I hope the shift is to really focus on this modularization aspect and then this notion of communication between the quantum devices. Without that, the world is going to be littered with hundreds of tiny little quantum computers that really don't do anything all that interesting.
Well, I'm going to go off my questions list just a little bit, but when I read about multi-core designs in your paper, I got really excited because one of the things that we've seen in classical computing is this advent and this increase in cores, right? Like, so I had an i7, which I believe had 6 cores, i7 MacBook a few years ago. And now I'm using the Mac Studio, which has 20 cores, right?
That's right.
So, but one of the advantages of that, like in the paper, you'd mentioned that you could break calculations up. So if you have an algorithm that requires like 100 qubits of calculation, you could use 5 20-qubit cores. But then it seems like the other advantage of that is if you're not doing calculations that require that depth, you could also independently task those cores, which is a lot how classical computers work, right?
That's right. And there are some ideas right now, they call it circuit knitting. It's a bit of a divide and conquer type of algorithm. Now, not everything is amenable to that, though. I must say that some of these algorithms, you almost really have to pretend like you've got this quantum computer with 100,000 or a million qubits. And this is where software comes in, right? I hope I'm kind of reminding you and the readers of some of the things we did classically. On the core side, 2005 was the first time Intel introduced a dual core computer. I had a PC for 20 years by that point, still laboring away with one CPU. And now, as you said, phones have multiple cores, supercomputers have thousands of cores. Well, we need to adopt that. But on the software side, software is going to become more and more important for quantum computing. You have to figure out how to use this hardware. So if I have a program right now for let's say my iPhone, somebody writes the source code, maybe me. It has to get translated. It has to get compiled into a form that the hardware can use. Now, some of these changes are, well, Bob did something dumb. He keeps doing something over and over again. He doesn't have to. We'll remove that. But other things are very specific to the hardware. What is the actual layout of the chip, the design? What instructions are there? So there's a lot of very advanced optimization that goes on today, classically, to make those chips hum, using the GPUs when we can, using the CPUs and so forth. Same is going to happen with quantum, and is beginning to happen as well. Infleqtion has a product called SuperStack, which does exactly this, which optimizes quantum circuits to run on different types of hardware. Not in a one-size-fits-all, but saying, all right, you're an ion trap, you're superconducting, you're neutral atoms. What are the core gates? What are your core operations? And how do we make these run as quickly as possible? And across cores, which makes it even more difficult.
All of these challenges take us squarely back to your paper. These are topics that you have, again, covered in depth there. And you had written that after 25 years of development, quote unquote, the industry faces a significant chasm as we try to scale our quantum computers to meet the promised solutions and breakthroughs in areas such as optimization, chemistry, and machine learning. So to me, when I read that, it sounds like a warning that the quantum computing industry is about to enter the Gartner hype cycle's trough of disillusionment. Would that be a fair statement?
Different people have different opinions on, depending on what you're selling, right? And what your view is. No, I don't think it's about to enter the trough of disillusionment. I kind of hope it's past the hype peak, if you will, right? There's another stage to that hype curve or whatever, where there's a little line that as it starts, the hype starts to decrease. Somebody figures out how to jump across the trough, right, to actual success. I'm trying to give some headlights, though, into the sorts of things that you will expect people will announce over the next few years as they work on these problems. And it's not all just about numbers and qubits. Look at my fancy, shiny new 24, a couple hundred, 1,000 qubits. There's a lot more to getting useful quantum computers.
Yeah, and again, the IBM system, Condor, is just over 1,000 qubits, which is tremendous compared to the version before that. But you are predicting 100,000 to 500,000, quote unquote, very high quality, long lasting, well connected physical qubits to actually exceed performance of a classical computer. So we're not even near that in terms of sheer qubits. And from what I understand, the quality, the coherence time, and the connections just aren't really there yet, right?
That's right. And I would consider that table stakes. I gave this paper at a conference at the Vatican, of all places. A lot of people were a little surprised. The Pontifical Academy of Sciences had a workshop on quantum technologies. It was an extremely non-commercial conference, and it was just talking about advances in the science, but also the impact that the science was starting to have on people. And part of my role with this paper was to bring, as you said at the top, some reality to all these types of predictions. I think we'll get there. We need a lot more cleverness. There is science to be developed. Anybody who tells you it's all engineering from now on, that's silly, right? But we're going to need, in addition to the science, some very solid engineering. And let me also say that speaking of the quantum industry in general, here we're talking about not just computers, we're talking about clocks, we're talking about sensors, quantum radio frequency receivers. Turns out you can use technology for that as well. We have to make it. A lot of these quantum devices that we're talking about, including computers, are, I'll use the term, lovingly handmade. That is, we put them together, we get the lasers, we get the glass cells, or even if we have the chips, we have to connect them in our golden chandeliers, right, and connect everything up. To really make quantum useful in the long range, right, across all these technologies, we have to learn how to manufacture them better, and we need to learn to manufacture them in quantity. So I didn't address that in the paper because I was just starting to look at how we get big enough computers. But this notion of manufacturability, right, is critically important. There are millions of smartphones, right? How will we get to hundreds, thousands, tens of thousands of quantum computers, clocks, and so forth? So there's much innovation across the entire technological life cycle, lifespan of all these devices that has to be done.
Yeah, many challenges. And then one of the other challenges, and I'm not sure if I'm expressing this correctly, but you had written that in terms of the input problem in quantum storage, there were concerns about no low-level operations to transfer data to or from quantum memory or storage. But there's an additional challenge because of the no cloning theorem, which says that we can move information, but we can't copy it, right? So in a traditional computer, a lot of the moving information basically is a copy process followed by deleting the original, right? In quantum, you can't do that. You actually have to move the states themselves, and you can't create those copies. So that adds kind of an additional scientific layer of complexity to an already existing technical challenge.
This is one of the fun oddities of quantum mechanics in class, in quantum mechanics in particular. Suppose you were an IT administrator and you had a database, and I say, I want to pull information out of your database, but by my doing it, it will destroy the database. Well, they might not let you use it very much, but in fact, that's everyday life in the quantum world. Quantum information cannot be copied. It can be moved around. And because of that, we have to get very clever. It's the reason why quantum algorithms are not the same as classical algorithms. You don't just take software that might run on your phone or your laptop and stick it on a quantum computer. The programming model is completely, fundamentally different. And that's why we get these fantastic terms like superposition and entanglement. Those are part of the model that we have to have. There's definitely work to be done on all of this, but we are learning more, doing an awful lot of education about quantum. And I will say, I've had the great opportunity to speak with teenagers, different times, just talking about coding, and software engineering. They don't have a lot to unlearn. I have 50 years of classical computing to unlearn and get through my head to think in a quantum way. So there's one great advantage of the generations coming up learning about computing is that they will be quantum natives in that regard. And I think we'll see a lot of innovation simply because of that.
Absolutely. And I want to touch on some of the silver lining aspects of this as well, because again, in the paper, you were outlining a lot of the challenges. And to be honest, when I read this, I was like, oh, geez, I feel kind of depressed. Let's think of some positives. So, well, no, it's all incredibly valuable things that need to be addressed, right? But then when I stopped to think about it, I said, well, what do we have going for us in terms of quantum computing that the classical world didn't? I think one of the big advantages is we have classical computers and they continue improving. And like, again, using my Mac as an example, even though we are pushing Moore's Law, some people have said that we've actually passed Moore's Law. Companies like Apple and many others are getting around that by increasing the number of cores, increasing the bus speed, basically improving memory access times, as well as creating specialized circuits, right? And we see like neural networks for face recognition and things like that. So classical computing continues to move forward. It's not like we've hit this bottleneck where we said, okay, that's it, we're stuck until we have some kind of replacement, right?
And we just have that experience. Many people, including me, date the beginning of the classical computing era to about 1945, let's say, more or less. Right? So we have almost 80 years of experience. Quantum computing is not starting from scratch. Right? Elements of software engineering come in just in slightly different ways. Before we talked about cores. Well, classical cores came in 2005. Now they need to come in for quantum. Optimizing compilers have been around for a while for classical. Now they need to come in for quantum. The software stack, classical looks eerily familiar to what we're going to need with quantum, and moreover, they have to work together at the top. So we do have all that knowledge, right? We don't have to wait 80 years, right? We can build on what we know. There's a lot of investment right now that's going on in quantum computing in particular. it does bring us a little bit to the question, though, that I hit at the end, and I tried to hit very carefully about startups in quantum computing. And I tried to address workforce in a slightly different way. So workforce is basically, do you have the people you need to either run your business or develop the science, develop the engineering, whatever. Good, skilled, smart people to do whatever you want to do. And you hear a lot in the quantum industry that there are just not enough people. Well, what sort of people are you looking for? Well, a lot of times these people are physics PhDs. Well, you can kind of see there are only going to be so many of those. But as we move forward, this notion of quantum engineering, hardware, and quantum software engineering, we talked about manufacturing. What's going to be different about that? So we need people with all sorts of skills. Now let's pause for a moment. And this was the point I tried to raise in the paper, which is if we keep making all these quantum startups to start at the beginning with slightly different flavors of the technologies we have, we are diluting the workforce, right? There's a finite number of really smart, talented, skilled people that we can apply to this problem. And I know everyone maybe has a dream of doing a startup and getting rich and being bought by this person or that. But there's a lot more that goes into this than reinventing the very basic wheel all the time. And as the paper points out, there's a lot of technology we have to develop, new technology, to build these big, powerful machines. That isn't how I make 5 new qubits, right? I'd love to see more of this expertise go into this scaling problem, right? Not the basics, but the really smart, skilled people come in and look at transduction to connect cores and for networking, right? New types of three-dimensional scaling of these sorts of systems. So if you're looking to do a startup, I'm really sorry to have to say this, but maybe you should go work for an existing quantum computing company and help them become successful. This will speed up. So the right workforce on the right type of advanced technology to actually get us computers we can use, right? Instead of more little computers.
Absolutely. Well, I look at the workforce aspect of this as potentially being a tremendous silver lining. I went through the dot-com boom, and one of the things that I saw in Redmond was there was this labor shortage that drove, I mean, so many people went into education to get the specialized skills, certification processes to develop, the work skills in a rapid pace. It also just drove on-the-job training and basically lots and lots of good paying jobs where people were valued and respected and were really able to challenge themselves were just created overnight. And what you're describing with quantum computing, it sounds like that could be very similar to that, right? Where you had the advent of this new technology, you have this rapid boom and need for jobs, and that comes on top of classical computing, which continues to expand in terms of networking and mobile applications and things like that. So it seems like this could be a tremendous value add in terms of quality of life, good paying jobs, family stability, all of those things that we hope for in our workforce. So I hopefully I'm viewing that as a silver lining.
I think so too. It's interesting you mentioned the dot-com boom and then bust. Let's not forget.
Yes, boom and then bust.
I don't think it was the first time ever used, but irrational exuberance in the investment community, right? Yes, we need 17 different online pet stores. Well, maybe not. But if you remember, once it started to quiet down, after the bust, 2001, 2002, things seemed a little quiet for 4 or 5 years. That is, people put their heads down. You mentioned got the education. They were less concerned about the flashy hype and things like this, but they'd gotten many good ideas about how the technology could be used. It was the transference of the notion of the web, which started as just web pages, right, to actually using it for business. And that's what we started to see. And so by the time we got to 2007, which was a very good year technology-wise, the iPhone was introduced. Deep learning came along roughly in 2007. And then as we went on the next few years, cloud computing opened up even more than it had. Amazon, I believe, started cloud computing, AWS, more or less in 2002. So yet something else that came later. So everything I say in the paper and generally, I want to repeat, I'm optimistic. I just want to give headlights. It's time to put our heads down and tackle the real problems, the problems that will get us to all these great promises, these use cases we've heard about. And I think that's what we're seeing. I hope we're seeing. Hype will continue. Some of it's just cringeworthy. There's been a little bit of that recently, but good, smart people focusing on the work that has to get done will get us across that chasm, right? From little computers to big useful ones.
Well, and before we wrap things up, I do have to mention the mother of all hype effects, which is AI, right? I mean, and I think that's stolen a lot of the thunder that would have gone into quantum computing. People, they look at quantum, it's confusing. They say, okay, this is obviously a few years off. And then they have ChatGPT, which is doing homework for kids right now, So but I think the other part of AI is, as that surges forward, I mean, investment dollars are pouring into AI. We can use that to hopefully help design quantum chips, right? In various ways. It can also hopefully assist with this, potential labor shortage that we see in the future. So
AI is sucking up an awful lot of the resources. It's sucking up a tremendous amount of the investment money that's going on. When we think about AI, well, let's even just specialize it for machine learning. Among the parts of AI, let's think of that. Your use case is the one that people often forget about. That is using machine learning to make quantum better. And yes, you will see that to design chips better. You'll see that to design algorithms better. A number of different things to reduce the amount of noise that's actually in the hardware. I've seen examples of that. So machine learning as part of AI is a general purpose tool. It makes perfect sense to apply that today. Now, the other way, which people talk about, and I think tremendously overhyped, is how are we going to use quantum for AI? Well, I got two buzzwords in that sentence, so I'm more likely to get a grant or funding, right? I've got AI and I have quantum. But quantum cannot today use very much data, the input problem. I cannot ingest a tremendous amount of information and then process it with a quantum system. So how useful is using a little bit of data, right? And why would I need a quantum system? Well, the answer is you don't yet, right? And that's why we have to get much more clever, right? Whether it's quantum memory, whether it's the networking, whether it's increasing coherence time, the general speed of the systems. So I do think this combination of quantum for AI is one of the most hyped areas, sorry to say, that we're seeing. We're seeing good research, right? People are learning things, but it's research. It's not development. And it's certainly not in production.
Yeah, it's chaotic. It's difficult to know where things are going, but at the same time, tremendously exciting. It's a whole new world, but it'll take a while to get there. Bob, let me thank you so much for your time today. Again, truly a pleasure and an honor to have you with me. So let me close by asking, what is coming up for you in the next few months, and what do you see happening for quantum computing in the early part of 2024?
Well, for me, I've just finished teaching a graduate seminar in quantum, which was fascinating to do. It's nice to get back to some of my teaching roots. I, of course, have a role with Infleqtion. Another side project, though, is completing the second edition of my book, Dancing with Qubits. I started the first edition 2018. It came out about a year and a half later. And I'm hoping in this first quarter of next year, the second edition will be out. In addition to the normal sorts of things of improving the exposition and saying a little bit more that you should have said in the first place, I have added a couple of chapters on so-called NISQ algorithms, as well as quantum machine learning. So I survey those topics. Each of those, you could have books, and you do have books and books and books on those sorts of things. So it's really the idea to give people a flavor, but also a little bit of the heads up. We've discussed at a high level some of the things regarding that. So I'm looking forward to that coming out. Next year, I think it's going to be very interesting. I think we've laid the groundwork, many other people, not just me, about this connection of optimism plus reality. That's what I want to end 2023 with. Optimism plus reality, right? What does that really mean? And I think our discussion here sort of encapsulates all of that. Next year, I think we'll continue to see a focus on other types of quantum technologies. I do think we'll get deeper into some of these corners we've talked about. Networking. I think quantum networking is going to be key to make all of this work somehow, some way. So I'd like to see much more focus on that. So
wonderful. Bob, let me thank you again so much for your time today, sir.
It's a pleasure, Tim, and I always enjoy speaking with you.